water. Water is both miraculous and at times mysterious. As a chemist, you could choose to study water and further understand the intricacies of its behavior for your entire career. To look at something that plays a role in all our acid-base behavior. We said, acids really don't show themselves as acids and bases as bases until they're in an environment of water. But water, if we have a sample of pure water, that's actually not all that we have, we can measure that a very small percentage of the water molecules behave as acid, and then others behave as base. So behaving as acid, we know water will donate the hydrogen ion. If it abandons, or a hydrogen ion abandons, then we'll form hydroxide. And then if this accepts, we form hydronium. So there's a very small percent of acid and base that react to actually create the species that, we say make something a base and make something an acid. So we have to realize in the background of acid-base behavior, for example, HF in water, that there's some water in the background doing its own thing as well. But if we just have a sample of water at room temperature, well, we can describe this equilibria with a K expression. But the K expression, because our reactant molecules are in the liquid state, does not have a denominator. It is simply the concentration of hydroxide times the concentration of hydronium. And if it is pure water at 25 degrees Celsius, the concentration of this will be equal to the concentration of this. And we find that K is 1 times 10 to the minus 14th. Of course, it would be molarity squared, but we know we don't keep units with that. So, if we are at room temperature, which we will be with our acid-base reactions, we can rely on this equation if we know the hydroxide to get hydronium or hydronium to get hydroxide. We, of course, could write this as hydrogen ion. Now, water is one of our go-to amphoteric species where it has the ability to behave as acid and base because of formula. It contains a hydrogen ion that it can release, but also a species that could accept the hydrogen ion. Notice I put that little KW there without explaining. So this officially is the ion product constant for water. We could call it dissociation or ionization constant, but this is describing the behavior of water. And because, again, we're going to have water in the environment of acids and bases, then we can rely on this to help us out to find concentrations of hydroxide or hydronium where otherwise we couldn't. So, K will be the same. I really think I'm just going to just show this to us, and then we'll come back to this whenever we are delivering and looking at some acid-base equilibria. But, if we have water, what we understand in a neutral solution, what makes it neutral, or a pH of 7, is that the concentration of hydroxide is equal to the concentration of hydronium. Well, in an acidic, that must be a situation where the hydronium ion concentration is greater than the hydroxide. And then in basic, it must be that the hydroxide is greater than the hydronium. And again, we'll come back to this idea when we look at pH, when we look at weak acid equilibria. The most important thing from this video is to realize that when we have water, some of the water molecules are reacting with other. Now, not very many. Again, if we think about in several liters of water, that we just have concentrations, if it's pure water, of at room temp 10 to the negative 7th and 10 to the negative 7th molar. That's pretty minuscule, but enough to help us out with this equation in terms of calculations. And we see how low this value is. And so we, of course, are grandly favoring reactant. This is just another illustration of an amphoteric species where something has the ability to be both an acid and So remember this equation and Kw, and we can refer to this whenever we need it. This should never limit our sig figs in calculations.